Imagine a world where the most challenging computational problems, ones that currently take enormous amounts of time and energy to solve, could be tackled swiftly and efficiently, all without relying on massive power-hungry machines. Sounds like science fiction? Well, researchers at UCLA and UC Riverside are making it a reality with a groundbreaking leap in computer hardware technology. Their innovation could completely transform how we approach complex optimization challenges, from designing telecommunications networks to optimizing traffic systems and beyond. And this is just the beginning. But here's where it gets fascinating. Instead of relying on traditional digital processors, which are increasingly constrained by physical limits like size reduction and energy consumption, this new system harnesses the power of quantum oscillators. These oscillators work together in a network, creating a novel computing framework inspired by statistical physics, an area of study that deals with large-scale systems and their behaviors. By encoding data and constraints into the phase relationships of these oscillators, rather than using explicit digital states, the system can naturally compute thousands of potential solutions simultaneously. The result? A dramatic improvement in efficiency and speed, solving problems that were once considered nearly impossible. At the heart of this breakthrough lies a specially engineered material called tantalum sulfide, part of a family of substances known as charge density wave, CDW materials. What makes these materials so remarkable is their ability to exhibit unique quantum properties even at room temperature, a stark contrast to most quantum computing technologies that require near absolute zero conditions to function effectively. This distinction is monumental because it eliminates the need for costly and cumbersome cryogenic cooling systems, making the technology far more practical and scalable for everyday applications. But what does this mean for industries like logistics, finance, or even healthcare? Could this be the key to unlocking unprecedented levels of efficiency? The implications of operating at ambient temperatures cannot be overstated. Not only does this approach sidestep the logistical nightmares associated with maintaining ultra-cold environments, but it also opens up possibilities for integrating quantum-inspired effects into existing silicon-based platforms. Traditional semiconductor devices manipulate electrons through logic gates, requiring intricate designs and hefty energy expenditures. In contrast, the oscillators developed in this research leverage the intrinsic quantum states of the material itself to perform calculations. This fundamental shift in how computation happens represents not just an evolution, but a revolution in hardware design. One that bridges condensed matter physics and information processing seamlessly. To bring this vision to life, the team utilized advanced nanofabrication techniques at UCLA's Nanofabrication Laboratory to create arrays of coupled CDW oscillators. During experiments conducted in the Phonon-optimized engineered materials lab, these devices demonstrated spontaneous synchronization or phase locking, corresponding to solutions for combinatorial optimization problems encoded within their interactions. This synchronization reflects the system's ability to evolve toward a ground state, where all oscillators operate in perfect harmony, effectively finding optimal configurations with remarkable efficiency. Rigorous testing confirmed theoretical predictions, showcasing the robustness and reliability of the technology. One of the most exciting aspects of this research is its potential to merge quantum mechanics with classical electronics. Tantalum sulfide's dynamic switching between electrical conductivity and vibrational modes provides a natural platform for encoding information and performing computations. Unlike conventional semiconductors, which rely on transistor-based logic gates, these devices compute directly through the material's inherent quantum behavior. This dual capability paves the way for hybrid computing architectures that combine the strengths of both classical and quantum-inspired approaches. But here's the controversial question. Does this mean we're witnessing the dawn of a post-digital era where traditional binary logic gives way to entirely new paradigms? Energy efficiency is another cornerstone of this innovation. Today's computing systems consume vast amounts of electricity, contributing significantly to global energy demands and environmental concerns. By leveraging the natural tendency of oscillators to synchronize into low-energy ground states, this system drastically reduces the need for energy-intensive processing steps typical of classical computers. This feature is particularly relevant for edge and embedded computing scenarios, where resources are limited and energy conservation is critical. Could this technology help pave the way for greener, more sustainable computing practices worldwide? While the initial focus has been on combinatorial optimization problems, the underlying principles of this oscillator network hold promise for tackling broader classes of challenges. Think machine learning algorithms, cryptographic protocols, and perhaps even simulations of complex quantum systems. The research team envisions further refinements aimed at enhancing coherence times and scaling the networks, pushing the boundaries of performance even further. With funding from prestigious organizations like the Office of Naval Research and the Army Research Office, this work underscores the strategic importance of developing powerful yet energy-efficient computing paradigms for defense and national security applications. Published in the esteemed journal Physical Review Applied, this research not only advances our understanding of quantum-inspired computing, but also sparks important conversations about the future of information processing technologies. As we stand on the brink of what could be a paradigm shift in computing, one thing is clear. The fusion of quantum physics, material science, and nanotechnology offers a promising path forward. So what do you think? Are we ready to embrace a future where quantum-inspired hardware becomes mainstream? Or will resistance to change slow its adoption? Share your thoughts in the comments below.